Today we're going to start talking about magnetism in chapter 26. If you notice where we are in the course, we're getting down towards the end. We're in our last section here. And in this part of the course, we'll be talking about magnetism as a separate phenomenon, but then we'll be tying it in with electricity to talk about electromagnetism and ultimately electromagnetic waves. So you guys already know all the basic stuff about magnetism. You know that there are two types of poles, which we call north and south, that like poles repel and opposite poles attract. So you'll notice that it sounds a lot like electricity, where we have two types of charge, positive and negative. And we know that like charges repel and opposite charges attract. So it seems very similar to what we have with electricity. So here's a question though. What happens if you take a magnet and you break it in half? Do you end up with just an isolated north or south pole? What do you think? Well, it turns out that you don't. In fact, if you take a magnet and you break it in half, what you find is you now just have two magnets. And if you take those and break them in half, you now have got four magnets. It turns out that even if you get down to just one atom, you still have a north and a south pole. So even an atom can act as a magnet. So notice how different this is from electricity. In other words, in electricity, we can easily have just a positive charge or just a negative charge, like a proton and an electron. In magnetism, we never have just a north without a south. The way that physicists refer to those are magnetic monopoles, mono meaning one, and so no magnetic monopoles have ever been found. So magnetism has some similarities with electricity, but it's definitely not the same thing. In a similar way to electricity, magnets create magnetic fields. So just as charges create electric fields, magnets create magnetic fields, and they surround a magnet just like electric field lines surround charge. In the same way, we're going to represent how strong a magnetic field is by drawing magnetic field lines, just like we did for electricity. Now, the one thing we do have to define is the direction. Remember that for electric fields, we define it as the direction of the force on a positive charge, right? The electric field is defined as F as the force divided by Q, where Q is a positive charge. So for magnetism, once again, we just have to choose a standard and stick to it. We say the direction of a magnetic field is defined by the direction of the force on a north pole placed in the field. Now, of course, we never just have a north pole. What we have is a north and a south pole that we could test with, and that's what a compass is. If you think about a compass, it's just got a little needle here, and one side of that needle is the north pole, and the other side is the south pole. And so what we're saying is the direction of the field would be the direction that the north pole is urged. So the compass is always going to align with the magnetic field, and the north pole will be in the direction of the field at that point. So let's review what we know about electricity. This is a key thing that I've been stressing to you over the semester. Electric charges produce electric fields. And of course, here is the simple formula for the electric field created by a point charge. Remember that if you just know that much, you could theoretically figure out the electric field of any array of charges just by adding up the electric fields from all the individual charges. So charges create electric fields. We also know that if we put a charge in an electric field, it will experience a force. So what we now want to look at is what is the equivalent for magnetism? If electric charges create electric fields, what creates magnetic fields? Well, you might be saying magnets. But it turns out it's not that simple. It turns out that fundamentally all magnetic fields are created by moving electric charges, or another word for that, of course, is currents. All magnetic fields are created by moving electric charges. Now you might say, well, but what about the magnetic field of a simple bar magnet? Well, it turns out it's the movement of the electrons in the atoms of that bar magnet that is actually creating the magnetic field. So there is no stuff that creates magnetic field. There's charges that create electric field. There's no equivalent stuff that creates magnetic field. Instead, it's simply the movement of electric charges that create magnetic fields. Okay, so what we want to start figuring out is, well, how do we describe that with a formula that charge creates magnetic fields? Also, it turns out that if you put a moving charge in a magnetic field, it will experience a force. Okay, and so we want to figure that out. And that's actually kind of where we're going to start in this chapter. So moving electric charges create magnetic fields. If you put a moving electric charge in a magnetic field, it will experience a force. I want to just remind you how simple, relatively speaking, the force is due to an electric field. Notice that we've got a vector equation, and that means that simply the force on the charge is directly in the direction of the electric field if it's a positive charge, and simply opposite of that if it's a negative charge. So you put a charge in an electric field, the force is either in the direction of the field or opposite. It's that simple. Not quite so simple when we get to magnetism. And in fact, we have to take a brief break from physics to talk about a mathematical concept. What we want to talk about is the vector product or cross product of two vectors. I want to just remind you that we know of one way to multiply vectors already. That's what we call the dot product or scalar product. And of course, we've seen this a lot in different contexts throughout the year. We know that in general, if I have vector A and vector B and I do the dot product of those, the value is given by A, B cosine theta, where A and B are the magnitudes, and theta is the angle between A and B. Okay, so you'll notice that with a dot product, and hence the name, what we end up with is just a number. It's a scalar. But it turns out there is a way to get a vector when you multiply two vectors. That's the cross product. So that's what we're going to be talking about. Okay, so first of all, the magnitude of the cross product, meaning the magnitude of the vector that you get when you multiply vector A and vector B, is given by this formula. So you'll notice instead of cosine, it's sine. Again, A and B here are simply the magnitudes of the two vectors. Remember, that means always positive. But what's more challenging about the cross product is to figure out what is the direction of this new vector. Where is C actually pointing? Well, to figure this out, we introduce something called the right-hand rule. Okay? So the direction of our new vector, the resultant vector C, is perpendicular to both the original vectors. Now that's important to understand, that the two original vectors form a plane. Okay, if you've got a vector like this and a vector like that, vector A and vector B, notice that those are both in the plane of the screen. So here's the key thing to understand about the cross product. Vector C is, since it's perpendicular to both A and B, that means there are only two possible directions for it. It's either straight out at you or straight into the screen. That's it. What the right-hand rule is used for is simply to figure out, is it coming out or is it going in? And by the way, I'll just introduce this notation now. A circle with a dot in the middle is a vector coming out towards you. A circle with an X in it is a vector that is going into the screen. Okay, so let's talk about how we use the right-hand rule. It's pretty straightforward, but it takes some practice. Please come to the online office hours because then I can easily demonstrate this for you. So as you get into this material, please take advantage of that. Okay, so anyway, you put your index finger, your first finger in the direction of vector A, your second finger in the direction of vector B, and then your thumb gives you the direction of vector C. So let's all try it together. Let's say that vector A is straight up, and let's say vector B is in this direction. So try orienting your first finger in the direction of A. Don't worry about how your hand is oriented. Now, twist your hand so that your first finger can still stay in the direction of A, and your second finger is in the direction of B. And now notice, is your thumb going in or pointing out towards you? Your thumb should be pointing towards the screen. And that tells us that vector C is in. Remember that when you use the right-hand rule, you're only trying to differentiate between, in this case, in or out. Since A and B are both in the plane of the screen, the answer is either into the screen or out of the screen. That's all you're figuring out with the right-hand rule. It's not like you're trying to come up with some direction in three-dimensional space, from nothing. So how does this apply to charges in a magnetic field? First of all, I should remind you that the letter we use to represent magnetic field is B. Okay, so B stands for magnetic field. If we look at this formula for the force on a charge in a magnetic field, you'll notice the force is both proportional to the amount of charge on our particle that's moving and its velocity. Again, remember, it's moving charges that experience a force in a magnetic field. Okay, so we've got a cross product, and that means that if we want to find the direction of that force, we know that it's going to be both perpendicular to the velocity of the particle and the magnetic field. When we use the right-hand rule for a cross product, again, our first finger is in the direction of the first vector, our second finger is in the direction of the second vector, and our thumb is in the direction of the resultant vector. So let's do a couple examples here and see how you do with it. Let's say our particle is moving in this direction. So that's the direction of V. And let's say that it's moving in a magnetic field that is in to the screen. So put your first finger in the direction of put your first finger in the direction of V, and now orient your hand so you can keep that finger pointing that way, and your second finger points into the screen. Okay, so your first finger is pointing straight up along the screen. Your second finger is pointing directly into the screen. You should see that your thumb is pointing to the left. And so the force would be in this direction. Again, always think about what is the plane being defined by V and B, and then know F is simply perpendicular to both, and you use the right-hand rule, in this case, to figure if it's to the left or to the right. Here's another example. Let's say that the particle is coming straight out at you. This one's a little hard. You got to point your first finger straight towards you. And now let's say that it's in a magnetic field that's pointing to the right. So first finger straight at me, orient my hand so I can have my first finger pointing at me and my second finger pointing to the right. What you should see is that your thumb is pointing up along the screen. In other words, the force on the particle would be like that. Again, if you're having trouble kind of visualizing some of this, make sure to come to the online office hours and we'll go through it where I can actually show you my hand at the same time. Okay, so we know how to find the direction of the force. The magnitude of the force for any cross product is just the vectors times the sine of theta. And so here, we're going to write the magnitude this way. We've got Q in an absolute value because, again, we just want a magnitude, and then the magnitude of the velocity and the magnitude of the magnetic field. So, what are the units of magnetic field? Well, we can figure that out from this formula. We can see that B is equal to the force that the magnetic field exerts divided by the charge, the velocity, and the sine of theta. Well, we know the units of force are newtons. We know the units of charge are coulombs, and the units of velocity are meters per second. But now I'm going to rearrange this a little bit. We know that magnetism has something to do with moving charges or currents. So you'll notice that I can rewrite this as newtons over coulombs per second times meters. Well, a coulomb per second is an amp. So we define a Tesla to be a Newton per amp meter. Okay, so our unit of magnetic field is the Tesla, and it's equal to a Newton per amp meter. By the way, I'll just make a quick note for you here. There's one homework problem that gives you the magnetic field in Gauss. A Gauss is related to a Tesla. One Gauss is 10 to the minus fourth Tesla. Okay, so you'll just need that for one homework problem. Otherwise, I'm not going to use that unit. Tesla is our MKS unit for magnetism. Okay, let's take a look at an example of an electron gun. An electron gun is what's in the back of an old-fashioned TV set or old-fashioned computer monitor. And what happens with this is we put a current through a filament, and as that heats up, electrons are boiled off that filament. They come off. And then we put a potential difference across between the filament and our disk here with a hole in it, and that's going to accelerate the electrons, and that's how we get our electron beam. And you'll remember we talked about this idea back in chapter 22 when we were talking about electric potential. What I want to do is I want to think about how a magnetic field would affect this beam. Okay, so we've got our beam of electrons going this way. Let's say that there's a magnetic field in this direction. So that's B, here's V. Go ahead and see if you can use the right-hand rule to figure out the direction of the force on that beam. Okay, so to help you work through it, I'm putting my first finger in the direction of V, my second finger in the direction of B. So I got to rotate my hand. And if you'll notice, from the right-hand rule, you're going to get that the force is out. However, that's actually not the correct answer in this problem. So it's actually not that because this is a negative charge. So since the force is QV cross B, notice that whenever the charge is negative, that's going to flip the direction of the resultant force. So the correct answer is that the force would be in to the paper because the charge is negative. So there are a couple different ways that we can deal with this. Either when you have a negative particle, use the right-hand rule and reverse the answer. Or the other way is use your left hand. Because you'll notice if you hold your two hands up, they give you the opposite answer. And so usually what I do is when it's a negative particle, I use my left hand, and then I don't have to worry about reversing the answer. But you can do it either way. Obviously, just make sure you understand how to get that as your answer in this problem. Okay, so let's do some practice. You'll notice that in this region of space, we have a uniform magnetic field that's pointing up. And I'm giving you a whole bunch of positive charges going in different directions. And what I want you to do is see if you can figure out what is the correct direction of the force on each of these charges. Now, let me remind you of a really, really, really important hint. Remember that the resultant force is always perpendicular to both original vectors. So if you can remember that, you realize this problem is not as hard as you might think it is. What are the two possible answers? Well, the two possible answers are either in or out, right? It's either out of the screen, which is perpendicular to all of those vectors, or it's in. Now, there turns out that there's one more possible answer, which is no force. So you might want to pause the video here and see if you can figure out which of these charges would have a force in, which would be out, and which would be no force. Okay, so let's go through them. Looking at this one first, that's probably the most straightforward. First finger to the left, second finger up along the screen, and my thumb is pointing towards the screen. So it's in. And you'll notice that it's the same for these. Just the angle between your first two fingers is bigger or smaller. But your thumb is still going to be pointing into the screen. So all three of these are in. In the same way, you should be able to show that all three of these, the force is out. Now, these two are a special case. You'll notice that in one case, V is in the direction of B, and in the other case, it's opposite the direction of B. Well, remember, the magnitude of the force is given by Q VB sine theta. So if theta is 0 or 90, then the force is 0. Okay, so these would be no force. Let's take a look at the following problem. It says an electron has an initial velocity in the direction shown in a constant magnetic field. Now, the way I'm representing a constant magnetic field here is I'm showing you a bunch of circles with X's in it. All that's telling you is that the magnetic field is straight into the screen and it's constant. And it asks us to describe the motion of the electron. So first of all, we can see that initially our electron is moving to the right. Why don't you go ahead and pause the video and see if you can figure out the correct direction. Remember, this is an electron, a negative particle. Okay, so I'm going to use my left hand. I put my first finger in the direction of V, so to the right. I put my second finger, or I twist my hand, so my second finger is pointing in. And you should see that your thumb is pointing down along the screen, so that that's the direction of the force at that moment. Now, the next question is, how does the electron move? Sometimes when I ask this in class, students say, oh, it's going to just go like projectile motion. But that's not true in this case. And the reason is you want to think about the fact that the electron will start to move like this, but now when the electron is here, moving in that direction, notice the force is no longer straight down. The force is always perpendicular to both V and B. So as our electron keeps moving, notice that the direction of the force stays perpendicular to the direction of the velocity. And if what you had figured out on your own was that this charge will go in a circle, you are correct. And in fact, because the magnitude of the force isn't going to change, it's uniform circular motion. So remember, when we talked about uniform circular motion last semester, we learned a couple things about it. One is that the net force is always directly towards the center of the circle. So in this case, that would be the magnetic force. And the other thing is when an object is going in uniform circular motion, the acceleration, the magnitude of the acceleration is v squared over r. So let's try out the following problem. If the initial velocity of the electron is 2 times 10 to the 7th meters per second, and it moves in a magnetic field of 5.7 times 10 to the negative 3 teslas, what is the radius of the circular path? So you may want to stop the video here and try to solve it yourself. So we need the magnitude of the force. Remember, the magnitude of the force is Q VB sine theta. And V and B, since V is straight in and V is in the plane of the screen, theta is going to be 90 degrees here. And really, for almost every example we look at with this formula, that's going to be the case. All right, so I want to just use Newton's second law, that the net force is equal to the mass times the acceleration. The only force acting is the magnetic force. So on the left-hand side, I've just got Q VB sine theta. And on the right-hand side, I have m times v squared over r. So again, my acceleration is just v squared over r. And I can go ahead and solve this. Notice that the v cancels with the squared there, and I get r is equal to mv over q b sine theta. Plugging in the values, we've got 9.1 times 10 to the negative 31 kilograms times 2 times 10 to the 7th meters per second divided by 1.6 times 10 to the negative 19th. Notice I'm taking the absolute value of that times the magnetic field of 5.7 times 10 to the negative 3 teslas times the sine of 90. If you work that all out, you should get that r is 0.020 meters. Okay, let's talk about something called the cyclotron frequency. So I want to figure out what does, ultimately the frequency, but we're going to start with period. I want to figure out what the period of a charged particle as it's going around in this circle, what it depends on. Okay, so we've just figured out that r is equal to mv over qb. And notice that here I'm simply dropping the sine of 90 degrees since it's just 1. Well, we also know from uniform circular motion that v is equal to 2 pi r over the period. Remember, that's simply because an object goes around a distance of 2 pi r every revolution, so per period. What I want to do is I'm just going to plug in r into this formula. So I get v is equal to 2 pi over the period times mv over qb. And the v's are going to cancel out. I'm going to rearrange this for the period. And I get the period is 2 pi m over q times b. Now, if you were thinking about this ahead of time, you might realize that that's kind of an interesting result, because you'll notice it doesn't depend on v or r. So in other words, if I take a charge and I stick it in an electric field at some velocity, the period that it's going to take to go around once is independent of the velocity and the radius. So in other words, a particle given a smaller velocity, it's going to have a correspondingly smaller radius so that it goes around in exactly the same time as the one with a higher velocity traveling at a bigger radius. Now it turns out this is kind of a useful thing that we're going to see. Okay, so the cyclotron, and this is called a cyclotron, by the way, when you put charges in a magnetic field and they're going around in a circle. Well, we know that frequency is 1 over the period, so I'm going to just rewrite this now in terms of frequency. So it would be the charge over times the magnetic field over 2 pi m. And again, the important thing is that frequency, how many times per second the charge goes around, doesn't depend on R or V. Okay, so why do we care about this? What's useful about this? Well, it turns out that anytime we have a charge moving in a periodic way, it's going to create an electromagnetic field or electromagnetic waves of that frequency. Now, when we talked about wave creation earlier in the course, I mentioned that in an antenna, it's the electrons oscillating back and forth in the antenna in simple harmonic motion that creates the radio wave. But it turns out that we can have other types of periodic motion besides simple harmonic motion, and another is uniform circular motion. So if we've got an electron just repeatedly going around in a circle, it's going to create electromagnetic waves of that frequency. And it turns out this is how the microwaves are created in a microwave oven. You remember earlier in the course we talked about microwave ovens and how the water molecule dipoles try to continually align with the oscillating electromagnetic wave. Well, the way it's created is by doing this. We have something called a magnetron that simply injects electrons into a magnetic field. They go around in circles, and that's what creates the magnetic wave or the electromagnetic waves, those microwaves in your microwave oven.